The issue of the reasons for the ionic conductivity of solids was considered by Frenkel. He suggested that due to the thermal fluctuations, ion can acquire energy sufficient to leave the normal positions at the lattice sides and go to the interstitial positions. Interstitial ions can jump from the one interstitial positions to another. The remaining free lattice sides also jump, since neighboring ions can occupy these vacancies, freeing up the lattice sides. During displacement, interstitial ions and vacancies can meet and recombine. When an electric field is applied to a crystal, interstitial ions more often jump in the direction of the field than in the opposite direction. That is, a current flows through the crystal. The number of the interstitial ions increases with temperature. Interstitial ions are more easily formed in lattices with large voids, and small ions are easier to transfer to interstitial positions than large ions. The combination of a vacancy and an ion in an interstice is called a Frenkel defect. The concentration of these defects is proportional Silver chloride is a classic example of a compound with Frenkel defects. Comparatively, small silver ions pass into interstitial positions and determine the purely cationic conductivity of the crystals. But Frenkel defects are not the only type of defects in ionic crystals. Schottky showed that in a real crystal there may be no interstitial ions, and at the same time some of the lattice sides are unoccupied. Since in general the balance of electric charges must be observed, an anion vacancy corresponds to each cation vacancy. The combination of cationic and anionic vacancies in an ionic crystal is called a Schottky defect. Schottky defects are formed as a result of thermal fluctuations. Ions leave the lattice sides on the surface of the crystal, forming vacancies inside it. The process of current flow in such crystal can be considered as a sequential transitions of ions of the crystal lattice to a neighboring vacancy. In general, the mobilities of cationic and anionic vacancies are different, which predominantly determines the cationic or anionic conductivity. Lattice violations also arise with the addition of foreign substances. For example, when adding strontium chloride to a potassium chloride, some of the potassium ions at the lattice sides are replaced by strontium ions. Since the strontium cation carries a higher positive charge, the corresponding number of cation vacancies must appear in the crystal for the condition of electroneutrality to be fulfilled. At high temperatures, The intrinsic concentration of vacancies in the crystal turns out to be significantly higher than the concentration of vacancies induced by the presence of foreign ions. Therefore, the region of high temperatures is called the region of intrinsic conductivity, which we considered in the previous video. The condition of electroneutrality of an ionic crystal during the formation of a cationic or anionic vacancy can also be satisfied with the simultaneous removal or introduction of electrons. This gives rise to bodies with electronic conductivity caused by quasi-free electrons and positive holes. The Frenkel-Schottky theory makes it possible to obtain quantitative relationships between the conductivity and the concentration of defects. Therefore, we can calculate the number of defects by measuring the conductivity of a solid electrolyte. In sodium chloride, the concentration of vacancies is equal to 1 vacancy for every 10,000 cations. The low concentration of vacancies is one of the reasons that normal ionic crystals, even at high temperatures and in the presence of a small amount of impurity ions, have a conductivity not exceeding 1/10 of Siemens per meter. Since vacancies and interstitial ions are charged, it can be expected that they will interact with each other in the same way as ions in electrolyte solutions. Frenkel was the first to point out that this interaction can be described by the Debye-Huckel theory. The interaction of defects leads to a decrease in the enthalpy of their formation and affects the conductivity of ionic crystals.